Okay, so in this video, we're going to go over a problem from 2019 IMC, International Math Competition, number 3. And this is an interesting problem because it combines inequalities with your knowledge of real analysis. So it gives you some inequality that is satisfied by a twice differentiable function over interval -1 to 1, and it asks you to show another inequality involving integrals. So the key to know when you're trying to solve problems like this is that if you have a function f of x greater than or equal to another function g of x over some interval a to b, then if that is the case, then you can integrate from a to b and the inequality is going to be preserved. So we're gonna have to find a way to integrate both sides of this inequality. And because you have a second derivative, we might have to integrate that a couple of times, maybe 3 times, to get to the function itself. So probably twice because you have a second derivative. The problem, though, is that on the left-hand side, you have the variable x, and you can't easily integrate that when you have a product of x and f double prime. So if I could turn the left-hand side into the derivative of some function, then I would be able to, in fact, integrate that. So that reminds me of what we call an integrating factor when you're solving differential equations. So what we want is we want to multiply this by some mu, that this becomes derivative of some function. So clearly one of those functions must be f prime and the other function must be mu x. So this is gonna have to be the derivative of mu x. So in other words, we want 2 mu to be the derivative of mu x. So now we're gonna have to find mu that satisfies this. So this is plus mu prime x by just the product rule. And that gives you mu is equal to mu prime x. So now, this is going to be part of our scratch work, which we're trying to find a solution for now. So you would have to find some mu that works for this one. Of course, 0 is not a good option, but anything that works other than 0 would be good. So you could either do separation of variables and solve this one, or this is not very difficult to see that mu equals x works. Okay, so now that mu equals x works, we could multiply both sides of this by x, but the problem is my x could be negative, so I'll have to take 2 cases. But let's focus on the case when x is positive. If x is positive, we get 2x f prime plus x squared f double prime is greater than or equal to x. And that can definitely be integrated because this is going to be derivative of x squared f prime. And when you integrate that, you can integrate that from 0 to some perhaps t x squared f prime of x prime dx, and that is greater than or equal to 0 to t x dx. If you integrate that, you're going to end up getting t squared f prime of t is greater than or equal to, the other side gives you t squared over 2. Fortunately, t squared is positive, so you can, in fact, get rid of that. You get greater than or equal to 1/2. Okay. So that's nice, but we're still not there yet. So we'll have to take this and somehow turn that into the integral of x f of x. So maybe a good option would be to integrate that again and see what we get. So if you integrate that again, we get f of x minus f of 0 greater than or equal to, and if you integrate the right-hand side, again, from 0 to x, we get x over 2. Okay, so that's pretty good. But just notice that I'm using the fact that x is positive because I'm integrating from 0 to x. So the order of inequality is not, the direction of inequality is not going to change. Now we're going to multiply by x. Again, I'm using the fact that x is positive. And then I'll integrate that again, and I'll get the integral from 0 to, going back, I see that I have integral from -1 to 1, so I'll do integral from 0 to 1. Because that's the key that I really am looking for. And on the right, I get the integral from 0 to 1. Integral of x from 0 to 1 is 1/2. So that would be 1/2 f of 0. Plus integral of that from 0 to 1 would be 1/6. Okay, so that seems like very promising. We'll do the same thing for the other side as well, and then we'll turn that into a solution. Okay, so let's write down the solution now. So if x is positive, then 2x f prime of x plus x squared f double prime of x is greater than or equal to x. So that was given. Thus, x squared f prime of x prime is greater than or equal to x, which means the integral from 0 to t x squared f prime of x prime dx is greater than or equal to integral from 0 to t x dx. If we integrate that, we get t squared f prime of t is greater than or equal to t squared over 2, which means f prime of t is greater than or equal to 1. Okay, now that I'm at this point, I'm going to do the same thing for negative x and see what I get. If x is negative, then 2x f prime of x plus x squared f double prime of x. This time, I would have to change the direction of inequality, which means x squared f prime is less than or equal to x. Now we're going to have to integrate that from x to 0 this time. X squared f prime of x prime, and in fact from, say, I guess from t to 0. Dx is less than or equal to integral from t to 0 x dx. And integrating that gives you 0 minus t squared f of t is less than or equal to t squared over 2 minus t squared over 2, which means f of t is greater than or equal to 1 if t is negative. And both of these two combined, that tells you that, and this is f prime, that tells you that f prime is always greater than or equal to 0. So therefore, f prime of x is greater than or equal to 1 for all x inside the interval -1 to 1. So because of that, we can again go ahead and integrate to see what we get. So again, if x is positive, then we'll get f of x minus 0, f of 0. So I'll be a bit more specific as to how we obtain that. So by integrating, we get f of x minus f of 0 is greater than or equal to x minus 0. Thus, x f of x is greater than or equal to f of 0 times x plus x squared. Okay. And oh, I think I missed this one as 1/2. This should be 1/2. Okay, yeah. Okay, so this is x over 2. Okay, and then we integrate that from 0 to 1. So 0 to 1, x f of x dx is greater than or equal to x integral of 0 to 1, x f of 0 plus integral from 0 to 1, x squared over 2 dx. Which means integral from 0 to 1, x f of x dx is greater than or equal to f of 0 over 2 plus 1 over 6. We'll do the same thing if x is negative. If x is negative, then by integrating, we get f of 0 minus f of x is greater than or equal to 0 minus x over 2. Which means if I multiply by negative x, I get x f of x is greater than or equal to x squared over 2. Then we'll integrate both sides of this from x to 0. So I'll get, from negative 1 to 0. So I'll get from negative 1 to 0, x f of x dx is greater than or equal to, and I have so I multiplied by negative x, I have x f of 0 on this side. So I'll get this is greater than or equal to integral from negative 1 to 0, x squared over 2 dx plus negative 1 to 0, x f of 0 dx. So that means the integral from negative 1 to 0, x f of x dx is greater than or equal to, the first one gives you x cubed over 6, and that gives you 1 over 6. The second one gives you x squared over 2, so that gives you negative 1/2, so that gives you f of 0 over 2. And if we add these two up, adding this to star, we obtain the result. Negative 1 to 1, x f of x dx is greater than or equal to 1/3. And that's exactly what they asked us to prove.